Tonight, the sky looks calm, the sun looks ordinary, but in just a few minutes, a burst of energy can race across space, strike Earth's upper atmosphere, and quietly erase radio signals across half the planet. No fire, no explosion in the streets, just a silent blackout in the systems modern life depends on. Welcome to space science, where deep space stories unfold in a calm and cinematic way. Tonight's journey follows how a solar flare can darken communication, disrupt navigation, and remind Earth that it still lives under an active star. If this is the kind of space documentary worth watching, please like the video, subscribe to Space Science, and share it with someone who loves science, sleep-friendly storytelling, and the quiet mystery of the universe. Something strange is hitting the skies above the United States. Bright fireballs, sudden shock waves, and falling stones from space are leaving both witnesses and scientists searching for answers. Are these events truly becoming more common, or is modern technology simply revealing a hidden cosmic pattern that has always been there? Welcome to Space Science, where deep mysteries of the universe are explored with calm, clear, and fascinating science. Tonight, this documentary follows the journey from silent space to the American sky, and down to the meteorites that survive the fall. If this kind of deep space mystery fascinates the mind, please like the video, subscribe to Space Science, and share it with someone who loves science and wonder. High above the surface of the United States, where the air thins into a near vacuum, small fragments of rock and metal move through space in quiet darkness. These fragments travel around the sun, following paths shaped by gravity, often unchanged for millions or billions of years. In this region, far above clouds and weather, there is no sound, no wind, and no resistance. The motion of each object continues steadily, guided only by the gravitational pull of nearby bodies and the momentum it carries from earlier collisions or separations. As one of these fragments approaches Earth, its path gradually bends. The planet's gravity begins to draw it inward, increasing its speed as it falls toward the upper layers of the atmosphere. The object is still cold, unchanged in appearance, and invisible from the ground. Its motion remains silent. Observations indicate that many such fragments are no larger than small stones, though some reach sizes comparable to large boulders. It remains uncertain how many pass near Earth without entering the atmosphere, as detection at this distance is limited. At a certain height, often more than 80 kilometers above the surface, the fragment meets the first traces of atmospheric gas. This region contains extremely thin air, far less dense than at sea level. Individual gas molecules are widely spaced, and collisions are rare at first. The incoming object moves at high speed, often tens of kilometers per second, and begins to interact with these sparse particles. Each collision transfers energy. The surface of the object starts to warm. The heating process is not caused by simple friction in the usual sense. Instead, it arises from compression and rapid interaction between the object and the air in front of it. The air cannot move aside quickly enough, and it compresses, raising its temperature sharply. This heated air transfers energy to the surface of the object. The outer layer begins to change. Minerals start to melt. Small amounts of material may vaporize and stream away behind the object. At this stage, the object is still not visible from most locations on the ground. The light produced is faint and often lost against the brightness of the sky during daylight. At night, under clear conditions, the first signs may appear as a dim point moving rapidly across the sky. Observations indicate that only a fraction of incoming fragments produce light bright enough to be noticed without instruments. As the object continues downward, the density of the atmosphere increases gradually. The number of collisions grows. The transfer of energy becomes more intense. The surface temperature rises further, often reaching thousands of degrees Celsius. The outer layers melt more rapidly, forming a thin liquid coating that flows backward under the force of the airstream. This process is known as ablation, a gradual loss of material from the surface. Ablation removes mass from the object but also protects its interior for a time. The melting and vaporizing outer layer carries heat away, preventing it from penetrating deeply into the core. As a result, the inside may remain relatively cool even as the surface glows. This contrast between a hot exterior and a cooler interior is a common feature observed in recovered meteorites. The glow becomes stronger as more energy is released. The object now produces a visible streak of light, known as a meteor. The color of this light can vary depending on the composition of both the object and the surrounding air. Elements such as iron, magnesium, and sodium emit characteristic colors when heated. The air itself contributes light through ionization, a process in which atoms lose or gain electrons under extreme energy conditions. At higher altitudes, the meteor may appear as a steady, continuous line of light. As it descends further, the brightness can increase sharply. Some events produce fireballs, which are unusually bright meteors that can outshine the brightest stars or even the planet Venus. Observations indicate that such brightness often corresponds to larger or faster objects, though the exact relationship varies depending on composition and entry angle. The path of the object is rarely vertical. Most fragments enter the atmosphere at shallow angles, crossing long distances through the upper layers before descending deeper. This extended path allows more time for heating and ablation to occur. The trajectory appears as a long arc across the sky, sometimes lasting several seconds. In rare cases, particularly large objects can remain visible for longer durations. During this phase, the object experiences increasing stress. The difference in pressure between the front and the back grows. The surface layers weaken as they melt. Internal fractures may develop, especially if the object contains cracks or regions of different composition. Observations indicate that fragmentation often begins at high altitudes, though it may not be immediately visible from the ground. The surrounding air continues to compress and heat. A region of ionized gas forms around the object, sometimes called a plasma. This plasma contributes to the brightness and may produce a glowing trail that persists briefly after the object has passed. The trail can drift with upper atmospheric winds, slowly dispersing over time. From the perspective of the ground, these early stages remain distant and silent. The light arrives first, traveling at the speed of light. While any sound produced takes much longer to reach the surface, for many observers, the event appears as a sudden streak, bright and fast, crossing the sky without warning. In the upper atmosphere, however, the process unfolds gradually, shaped by physical laws that govern motion, heat, and material change. Instruments positioned on satellites and high-altitude platforms can detect these events more clearly. Sensors measure light intensity, track motion, and estimate the energy released. These measurements help scientists understand the size, speed, and composition of incoming objects. Observations indicate that many small fragments enter the atmosphere each day, though most are too small to produce visible effects at the ground. As the object continues its descent, the balance between incoming energy and material loss becomes more dynamic. The outer layers erode, the shape may change, and the path may shift slightly due to uneven forces. The interaction between the object and the atmosphere grows more complex. setting the stage for the next phase of its journey. The high atmospheric region thus serves as the first boundary between space and Earth, where silent motion becomes visible energy. The transformation from a cold, dark fragment into a glowing meteor begins here, guided by the gradual increase in air density and the fundamental processes of heating and ablation. Within this thin layer, far above the surface, the first signs of the phenomenon take shape. Across the United States, the sky presents a broad and changing field through which these events become visible, over mountains, plains, deserts, forests, coastlines, and cities. The night air seems still from the ground, yet far above, a bright object may suddenly cut across the darkness. The first impression is often one of speed and distance. The light appears without warning, moves with unusual force, and then fades. In this region of observation, the focus remains not on the object itself as a material body, but on the way it is seen from below across the wide span of the continent. The visible sky over the country is shaped by local conditions. Dry air in the western interior often allows greater clarity, making faint stars and passing meteors easier to see. Humid air in the southeast can soften contrast, while cloud cover in any region may hide an event completely. Moonlight reduces visibility for dim meteors, and city lights wash out the weaker end of the night sky. For this reason, many incoming objects pass unnoticed, while only the brightest fireballs draw immediate attention from a large number of people. When a bright event does occur, its appearance depends strongly on geometry. A meteor high in the atmosphere may be visible across several states at once, not because it is close to every observer, but because its altitude places it above a vast portion of the curved surface below. One person in a rural field may see it low in the western sky, while another hundreds of kilometers away sees it high overhead, and a third sees it near the eastern horizon. The same event can seem to travel in different directions depending on the observer's location. Observations indicate that this difference in perspective is one reason eyewitness reports often vary in their description of path and apparent distance. Brightness in the night sky is judged by comparison. A faint meteor may resemble a quick-moving star. A brighter one may rival the planets. A fireball can outshine the full moon for a brief moment and illuminate the landscape below. This intensity does not necessarily mean the object is very large. Speed, angle of entry, atmospheric depth, and fragmentation all influence how much light is produced. A relatively modest body can appear extremely bright if it breaks apart in a way that releases energy efficiently over a short interval. Color is another feature often reported by observers. Some describe white light, others green, yellow, orange, blue, or red. Part of this variation comes from the chemistry of the object, and part comes from the atmosphere through which the light passes before reaching the eye. Sodium can produce yellow tones, magnesium may contribute greenish-white light, and ionized air can add blue or violet hues. Near the horizon, the thicker layer of air between the event and the observer can redden the appearance. Much as it does with sunrise and sunset, human perception also plays a role, especially during brief, surprising events when memory forms quickly and imperfectly. The shape of a meteor in the sky is usually not a point but a streak. This is partly because the object moves rapidly during the short time the eye is gathering light, and partly because the glowing region around it extends behind the body. Some fireballs display a bright head and a tapering tail. Others appear as a bead of intense light followed by sparks or separate glowing points. In many cases, those sparks reflect fragmentation, where smaller pieces begin to diverge slightly from the main path. From the ground, this can resemble a brief spray of light. Duration matters greatly in how an event is experienced. Most meteors last less than a second. Brighter fireballs may remain visible for several seconds, long enough for an observer to follow their motion consciously from one part of the sky to another. This longer duration often makes the event feel slower than it truly is. In reality, even a meteor that seems to drift is moving at extraordinary speed. The distance involved is so great that the eye interprets a long path across the sky as a measured crossing rather than a violent plunge. The apparent width of the path can also be misleading. In clear, dark conditions, a bright meteor may seem thick, almost like a glowing rod. This appearance comes from the intensity of light and the way the human eye responds to brightness against darkness. A dazzling object spreads in perception. Cameras sometimes record a thinner path than observers remember. At the same time, long exposure images may show features invisible to the eye, including persistent trails, multiple fragments, and subtle changes in brightness along the track. Over the United States, reports of unusual sky events often cluster not only around actual meteor activity, but around areas with more observers and more recording devices. Suburban regions, highways, doorbell cameras, dashboard cameras, and automated sky monitoring systems all contribute to modern awareness. As a result, an event that might once have been seen by a few scattered witnesses now produces a dense pattern of reports within minutes. This can create the impression that the sky has become more active, though the change may reflect visibility and reporting rather than a sharp increase in incoming material. Perspective also affects the sense of scale. A meteor near the horizon may seem close to the ground, as though it is passing just beyond a distant hill or city skyline. In reality, it may still be tens of kilometers high and hundreds of kilometers away. This is a common feature of human depth perception at night, when familiar landmarks offer limited guidance. Brightness without clear distance cues tends to make objects seem nearer than they are. For this reason, eyewitness estimates of landing sites are often far from accurate when based on sight alone. Some fireballs leave a lingering mark in the sky. After the bright head fades, a pale, glowing trail may remain, twisted slowly by winds high above the earth. This persistent train can last for minutes in favorable conditions. It may shift shape, broaden, and take on a faint luminous texture against the stars. Observations indicate that such trails form when the passage of the meteor leaves behind ionized gas and fine material in the upper atmosphere. Their slow movement from the ground gives a rare visible hint of the motion of air in those otherwise invisible heights. The night sky above the continent is therefore not merely a backdrop. It is the surface upon which distance, angle, brightness, atmosphere, and perception combine. A single meteor becomes many different experiences at once, each shaped by place and conditions. From the desert southwest to the Great Lakes, from the Atlantic coast to the Central Plains, the same event may be remembered in different colors, with different directions, different durations, and different emotional weight. Yet beneath these differences lies one physical event unfolding high above, traced across the wide dome of the American sky. The bright path through the atmosphere is not a simple fall. It is a rapid passage through a layered medium that grows denser with every downward step. In the high, thin air, the incoming body begins to glow. As it continues along its course, the surrounding environment changes steadily. More gas molecules crowd its path. More energy is transferred in less time. What appears from the ground as a line of light is, in physical terms, a moving zone of compression, heat, erosion, and structural strain. A meteoroid is a small natural object in space, usually made of rock, metal, or a mixture of both. When it enters the atmosphere and produces visible light, it is called a meteor. If some part survives to reach the ground, that remnant is called a meteorite. In this section, the focus remains on the moving body during its fiery passage through the air, before any final fragments descend in darkness. Here the important process is not arrival at the surface, but the changing motion through the atmosphere itself. The object enters with great speed, often far faster than any machine built by human beings. Even the slowest natural entries are swift enough to produce severe heating. The faster entries produce even stronger compression of the air ahead. This compressed air becomes extremely hot and transfers heat to the surface of the object. The outer skin begins to soften, melt, and boil away. The loss of this surface material is the process called ablation. It is one of the central features of a meteor's visible path. Ablation does not happen evenly. It depends on the shape of the object, the angle of entry, the rotation of the body, and the arrangement of minerals or metal inside it. A smooth, compact body may lose material in a relatively steady way, while a fractured or irregular body may erode more unevenly. Small projections on the surface tend to melt away first. The object may gradually become rounder as sharp edges are removed. In some cases, the flowing molten layer is swept backward and stripped away in pulses, creating brief changes in brightness. As the meteoroid moves deeper into the atmosphere, it also begins to slow. This slowing is called deceleration. The air is now dense enough to push back more strongly against the body, and the loss of speed becomes more significant. Still, the change is not always obvious from the ground. The light often remains intense, and the path still appears fast. Yet the physical forces acting on the object are shifting. Kinetic energy, the energy of motion, is being converted into heat, light, sound, and mechanical stress. The angle of entry matters greatly. A shallow entry allows the object to travel a long distance through the atmosphere. In this case, the meteor may paint a long luminous arc across the sky. With heating and material loss spread over a broader path, a steeper entry brings the body through the layers of air more quickly. The energy is then released over a shorter interval and a shorter visible track. Both kinds of paths can produce bright events, but their details differ. Observations indicate that shallow entries are more likely to create long-lasting visible passages, while steeper ones more often produce abrupt, intense flares. Brightness along the path is not constant. Many meteors pulse, brighten suddenly, then dim, then brighten again. These changes often reflect fragmentation. As the outer layers weaken and the pressure on the front of the body rises, cracks inside the object can widen. A piece may split away. Fresh interior material is then exposed to the hot compressed air, and this new surface begins to ablate rapidly. The result is a burst of light. If several fragments separate in quick succession, the meteor may seem to flash or blossom along its route. Fragmentation is common because many meteoroids are not solid blocks without weakness. Some are ancient mixtures of minerals, metal grains, and small fractures formed over long histories in space. Others are rubble-like assemblies that have endured earlier collisions. When such bodies meet the atmosphere, the stress can exceed their internal strength. Pressure builds on the front while heating changes the properties of outer layers. The body begins to fail. One fragment becomes many. Each new piece then develops its own glowing path, though the pieces often stay close together at first. The trail behind the meteor can take different forms. Sometimes it's a narrow, bright line that fades almost at once. Sometimes it expands into a glowing train that lingers after the main object has vanished. The immediate line is created by the hot plasma and incandescent material in the meteor's wake. The persistent train lasts longer because atoms and molecules in the disturbed air remain excited for a short time before returning to lower energy states. Fine dust and vaporized material can also contribute. High-altitude winds may slowly bend and twist this fading mark, turning a straight path into a drifting ribbon. Color may change along the track as well. A meteor can begin in one hue and shift toward another as conditions change. Early light may be faint and pale. Later light may become greener, whiter, or warmer in tone depending on temperature, composition, and depth in the atmosphere. Fragmentation can introduce brief flashes of different color when new material is exposed. The surrounding air also changes with altitude, and that changing air influences the light emitted and transmitted. From the ground, these color shifts can appear delicate or dramatic depending on darkness and viewing conditions. As deceleration continues, the forces on smaller fragments become stronger relative to their mass. Small pieces lose speed more quickly than large ones. They also cool more quickly once their bright ablation phase ends. This creates a changing swarm of material along the path. The largest pieces may remain luminous longer, while the smallest are consumed entirely or fade from view high above the Earth. What remains visible is only part of the process. A large amount of matter may already have been lost as vapor, droplets, and tiny particles spread invisibly through the air. The visible path through the atmosphere is therefore a moving transformation. A cold body from space becomes a heated, eroding, fragmenting stream of matter and light. Motion is reduced, shape is altered, mass is stripped away. The path that seems simple from the ground is actually a sequence of physical changes happening in fractions of a second and across many kilometers of air. Each meter of descent brings denser surroundings, stronger forces, and more intense interaction between the incoming body and the atmosphere through which it passes. In this region of the event, the meteor is neither the untouched object of space nor the fallen stone of the ground. It is a transient thing made by passage itself, defined by motion through air. Its line of light records compression, heating, ablation, and breakage. The atmosphere shapes the journey continuously, and the glowing track is the visible sign of that shaping, drawn across the sky for a moment and then gone. After the bright passage across the sky, another part of the event begins to matter. Light reaches the ground almost at once, but the atmosphere continues responding long after the glowing path has formed. The moving body has forced its way through air at tremendous speed, compressing it, heating it, and pushing energy outward. That energy does not remain confined to the narrow line of light. It spreads through the surrounding atmosphere as waves of pressure. In this region, the event is no longer understood mainly through what is seen, but through what is felt and heard. A body moving faster than the speed of sound in air creates a shock wave. A shock wave is a sharp pressure disturbance, a narrow front across which air properties change suddenly. Temperature, density, and pressure rise abruptly at this boundary. In ordinary life, a smaller version of this process occurs around supersonic aircraft. In a meteor event, the speeds are far greater, and the path through the atmosphere can be very long. The result is not a single point of noise, but an extended source of pressure traveling with the object as it moves across the sky. From the ground, this delayed sound often arrives as a boom, a rumble, a distant roll, or a sequence of sharp reports. The form it takes depends on the height of the meteor, the energy released, the shape of the path, and the state of the atmosphere between the event and the listener. One person may hear a deep, prolonged trembling sound several minutes after the light disappears. Another may hear a sudden crack followed by softer echoes. Observations indicate that many eyewitnesses at first do not connect the sound to the earlier light, because of this delay and because the source lies so far away. The delay itself is simple. Sound travels much more slowly than light. A meteor seen high in the atmosphere may be tens of kilometers above the ground, and many more kilometers away across the landscape. Even a strong pressure wave needs time to move through that distance. This is why an observer may watch the sky fall silent after the bright trail is gone, only to hear the atmosphere answer later. In some cases, the wait is less than a minute. In others, it can be several minutes, depending on geometry and distance. As the meteor passes, the shock wave forms a three-dimensional pattern around its root. It can be imagined as a moving envelope of compressed air spreading outward from the flight path. When this wave reaches lower, denser layers of the atmosphere, it can refract, reflect, and weaken in complex ways. Temperature gradients, wind layers, humidity, and terrain all affect how the sound is carried. Warm and cool layers bend sound differently. Strong winds at altitude can guide it along certain directions and diminish it in others. Because of this, some communities hear a clear boom, while others at similar distances hear little or nothing. The pressure wave is not always created in the same way. A steadily moving meteor produces a continuous shock along its path. Fragmentation can add something more abrupt. When a body breaks suddenly, especially if it does so violently, the surface area exposed to the air increases at once, and energy release can spike. This may create a stronger acoustic signal. In some large fireballs, repeated fragmentation leads to multiple booms or a rolling sequence of reports. The atmosphere records each major disruption, and the ground receives those records as a staggered pattern of sound. There are also events in which the pressure change is strong enough to rattle windows, shake doors, or make walls seem to tremble slightly. This does not necessarily mean the object is about to strike nearby ground. It more often reflects the large amount of energy released high above and the efficient transmission of part of that energy through the atmosphere. A window pane responds readily to a passing change in air pressure. So does a lightly built structure in rural areas. Such vibrations may be mistaken for distant thunder, quarry blasting, or even a small earthquake. Only later, when reports of a bright fireball appear, does the cause become clearer. The lowest frequency part of this atmospheric response is called infrasound. Infrasound consists of pressure waves below the range of a normal human hearing. People do not hear these waves directly, but instruments can record them over very long distances. Large meteor events can generate infrasound detectable hundreds or even thousands of kilometers away. These signals are valuable because they help scientists estimate the energy of the event and compare observations from different regions. The atmosphere carries these deep waves efficiently, especially when upper air conditions guide them through channels of favorable temperature and wind structure. At audible frequencies, the sound of a meteor can seem surprisingly terrestrial. It may resemble thunder moving across the horizon. It may sound like a heavy object tearing through the air, though the true source remains far above. This resemblance is part of what makes such events unsettling. The sky briefly behaves like a place of impact and force rather than quiet distance. Yet the explanation remains grounded in fluid motion. Air has been compressed, disturbed, and set into wave motion by a body moving faster than sound, and sometimes breaking apart under stress. Pressure effects at the ground are often localized and uneven. A house on one side of a town may experience window shaking, while another house a few kilometers away does not. Valleys, building arrangement, local atmospheric structure, and angle to the source all matter. Even the same event can feel different within a small area. This is why scattered public reports often describe a confusing mixture of loud booms, faint rumbles, or no sound at all. The atmospheric path from source to listener is rarely simple. Scientists compare these reports with instrument data to understand the event more clearly. Seismic stations can sometimes register coupling between air pressure waves and the ground. Infrasound arrays record low-frequency arrivals. Microphones, home security systems, and other accidental sensors capture audible effects. Together, these records show that the atmosphere is not merely a passive background for a meteor. It is an active medium that transmits the event downward after the light has gone, translating high-altitude motion into delayed force at the surface. In this part of the phenomenon, the meteor becomes an atmospheric disturbance spread through air rather than a streak across the eye. The visible trail may last only seconds, but the pressure waves continue outward, descending through layers of the atmosphere and reaching human settlements as sound and vibration. The event is thus divided in time. First comes the silent light, then comes the slower answer of the air, carrying evidence that something fast and energetic has passed high overhead. What seemed remote becomes physical, and the distance between sky and ground briefly feels much smaller. Once the light has faded and the delayed sound has passed, the event enters another region of understanding. It becomes a matter of records. A bright fireball over the United States is now seen not only by human eyes, but by a wide and uneven network of instruments spread across the land. In this region, the focus rests on how the event is captured, compared, and reconstructed. The meteor remains high above, already gone from view, but its passage continues in data, in timestamps, in images, and in subtle signals preserved by devices that were never all designed for the same purpose. Human observation is often the first layer. A person standing outside at night may see a sudden streak and remember its direction, brightness, colour, and duration. Someone driving along a highway may notice the landscape flash bright for an instant, and then look upward just in time to catch the last part of the trail. A family near a window may see the sky light up, and then hear the sound later. These memories matter, but they are shaped by surprise, darkness, angle, and distance. Observations indicate that eyewitnesses often describe the same event differently, especially when estimating height, direction, and apparent landing place. This does not make such reports useless. On the contrary, they provide the first broad outline. When dozens or hundreds of people describe where in the sky the meteor appeared and how it moved, scientists can compare those accounts to identify a probable path. A report from one state may place the fireball low in the southern sky, while another from a neighbouring state places it high in the north. Together, such perspectives help define a corridor in space through which the object likely travelled. The strength of eyewitness evidence lies not in perfect precision from one person, but in patterns formed by many people at once. In the modern United States, cameras add another layer. Doorbell cameras, dashboard cameras, security systems, traffic cameras, and outdoor wildlife cameras operate continuously across large areas. Most are not aimed at the sky in any deliberate scientific way. Many have narrow fields of view, automatic exposure settings, and clocks that are not perfectly synchronized. Yet when a bright meteor passes, these ordinary devices often capture valuable information. A sudden wash of light, a streak near the horizon, or a shifting shadow across a driveway can help place the event in time and space. Dedicated meteor camera networks provide a more controlled record. These systems are built to watch the sky continuously, often using wide-angle lenses and precise timing. They record the passage of bright meteors against a known background of stars. From this, researchers can measure the direction of their motion more accurately. If two or more stations record the same event from different locations, they can reconstruct its trajectory in 3 dimensions. The lines of sight from multiple cameras intersect, and from that geometry scientists estimate altitude, path length, speed, and possible survival of fragments. Timing is especially important. Even a small error in the recorded time can complicate the reconstruction of a fast-moving object. Dedicated scientific systems therefore use careful calibration. By contrast, public cameras may drift by seconds or minutes. Analysts often correct these differences by comparing the observed light pulse with other known records or with the precise timing from astronomical stations. A single well-timed video can become a reference against which many less exact recordings are aligned. Weather radar sometimes contributes in an unexpected way. During the bright atmospheric phase, radar is usually not the main tool, because the meteor is too high and too fast for ordinary weather tracking to describe well. But if fragments survive and begin to fall more slowly, the radar may detect a cloud of descending material. This can happen after the bright phase ends and the surviving pieces enter a darker, thus slower descent. The radar return is not always easy to interpret, because the same systems also detect rain, birds, insects, and drifting debris. Still, under the right conditions, weather radar helps narrow the area where meteorites may have reached the ground. Infrasound stations and other low-frequency acoustic instruments extend the record beyond sight. A meteor that produces strong pressure waves leaves a trace in these systems, even if clouds or daylight prevent visual observation. The arrival time and strength of the infrasound signal help estimate the energy released. When several stations detect the same event, researchers compare the pattern to model how the wave traveled through the atmosphere. This can support or refine the path derived from cameras and eyewitnesses. Satellites also watch for sudden flashes in the atmosphere. Some orbiting sensors are capable of detecting brief, energetic events over broad regions of the Earth. Their records may include the time, brightness, and approximate location of a fireball. These data can be extremely useful, especially for remote events with few ground observers. At the same time, not every detection becomes publicly detailed, and not every event is captured in a way that allows complete reconstruction. It remains uncertain in some cases how much high-altitude information is available for open scientific analysis soon after an event occurs. The challenge in this region is not only gathering information but combining it. Each kind of record has strengths and weaknesses. Eyewitnesses provide broad coverage but limited precision. Public cameras offer accidental evidence with inconsistent quality. Dedicated scientific networks provide accurate geometry where they exist, but they do not cover every part of the country equally. Radar helps only in later stages and only under suitable conditions. Acoustic instruments detect energy but not always exact location. Satellite data offer wide reach, but sometimes limited public detail. The work of reconstruction lies in fitting these partial views together. Scientists begin by sorting reports according to reliability. They compare times, discard duplicates, and remove clear errors. They identify fixed landmarks in videos and determine camera orientation. They compare light curves, the changes in brightness over time, to signs of fragmentation. They use star fields, shadow direction, and known road alignments to estimate the path. Gradually, a more stable picture emerges. What began as scattered impressions becomes a measured atmospheric event. This process also reveals how modern awareness changes the human sense of rarity. A bright meteor may once have passed over a region, with only a few isolated witnesses. Now it can produce hundreds of submissions, many videos, and immediate discussion across large distances. The event therefore feels bigger, more sudden, and more collective. Yet this change often reflects the density of recording and communication as much as the physical scale of the meteor itself. The sky is being watched more continuously than in the past, and so its brief disturbances are now preserved with unusual detail. In this region, the fireball exists as evidence after it exists as light. The atmosphere no longer glows, but the event continues through human memory, electronics, sensors, and analysis. The witness at the roadside, the camera on the porch, the radar sweep, the infrasound trace, and the calibrated sky station all hold different fragments of the same passage. From these fragments, scientists build a path through the air and begin to understand what moved above the continent and how it moved, using the ground not as the site of impact, but as a field of observation spread beneath the sky. After the bright path ends and the main sound has moved across the land, some surviving pieces continue downward through the atmosphere in a very different way. The violent luminous phase belongs to extreme speed, intense heating, and rapid erosion. This next phase belongs to slowing, cooling, and descent. The object is no longer a meteor in the full visual sense. It becomes falling matter, dark or nearly dark, moving under gravity through denser air. In this region, the focus rests on the surviving fragments themselves as they leave the high-energy passage behind and begin the quieter journey toward the ground. Not every incoming body reaches this stage. Many are too small, too fragile, or too completely consumed by ablation to leave any solid remnant. Observations indicate that a large share of meteors end entirely in the atmosphere, their substance dispersed as vapor and fine particles. Only when a body begins with enough mass, enough internal strength, or a favorable enough path does part of it survive the fiery passage. Survival is not a simple matter of size alone. Composition matters. A dense iron-rich object may endure conditions that would completely destroy a weaker stony body of similar mass. During the luminous phase, the object often fragments. What continues downward may therefore be not one body but many pieces, each with its own mass, shape, and speed. The largest fragments generally retain momentum longer. Smaller ones lose speed more rapidly because the atmosphere exerts strong drag on them relative to their size. As this slowing continues, the heating rate falls, the brilliant glow fades, the surface ceases to boil away at the earlier pace. The fragment passes out of its bright meteor state and enters what is often called dark flight, a phase in which it continues descending without producing strong visible light. Dark flight begins only after the fragment has slowed enough that extreme compression heating no longer dominates its motion. At this point, the atmosphere acts less like a wall of energy and more like a resisting medium through which the fragment falls. Gravity pulls downward. Air drag opposes motion. Wind begins to matter more. The path may bend slightly as the fragment responds to air currents in different layers. A large piece tends to follow a steadier course, while smaller fragments can drift farther sideways before reaching the surface. Although the fragment is no longer glowing brightly, it is not instantly cold. Its outermost layer has been heated intensely, melted, and then rapidly cooled. The interior, however, may remain much less altered than expected. This is because heat has little time to travel inward during the short atmospheric passage. A meteorite that reaches the ground may therefore have a thin altered skin while its inner material preserves ancient minerals with surprisingly little thermal change. This contrast is one reason recovered meteorites are so valuable for science. They carry a surface shaped by entry and an interior that may still reflect processes from the early solar system. As the fragments descend through lower air, their motion becomes more familiar in physical terms, though still unusual in origin. They no longer move at cosmic speed. Instead, they approach a limit set by the balance between gravity and atmospheric resistance. This limiting rate is called terminal velocity. It varies with mass, shape, and density. A compact, heavy fragment falls faster than a small porous one. Even so, the final descent is much slower than the earlier atmospheric entry, and the enormous energy of the fireball phase is largely past. To observers on the ground, this stage is often hidden. The bright trail has ended high above, and the surviving fragments are too dark, too small, or too distant to be followed with the eye. In rare cases, especially when pieces remain hot enough or when the sky is very dark, a faint continuation may be noticed briefly. More often there is nothing to see. The event seems over, though the material is still descending. This hidden interval can last several minutes, depending on altitude and fragment size. During this time, the atmosphere quietly sorts the falling pieces according to their physical properties. Because fragmentation often happens while the body is still moving generally forward, the surviving pieces do not fall straight down beneath the point of brightest light. Instead, they continue along the general direction of travel while also descending. Larger fragments usually land farther along the path because they resist slowing more effectively. Smaller fragments lose forward speed sooner and fall short. This creates an elongated pattern on the ground known as a strewn field. A long scattering of meteorites aligned roughly with the final direction of flight. The exact pattern depends on winds, breakup altitude, fragment masses, and entry geometry. Wind becomes increasingly important in the later part of dark flight. Different layers of the atmosphere may move in different directions and at different speeds. Small fragments are especially sensitive to this layered motion. A strong crosswind can push them well aside from the idealized path derived from the bright meteor alone. For this reason, scientists searching for meteorites combine optical reconstruction with atmospheric models, using wind profiles to predict where different sizes of fragments are most likely to land. Even with these methods, uncertainty remains. A slight change in breakup height or wind structure can shift the expected fall zone significantly. By the time a fragment reaches the lower atmosphere, its outer surface may have developed a thin melted coating that cools into a dark crust. This crust forms during the final moments of intense heating and then hardens quickly. It is usually thin, often only a narrow skin over the original material. While the fragment falls through cooler air, this skin continues to lose heat. The idea that meteorites commonly arrive red-hot and capable of starting large fires is not supported in most ordinary falls. Observations indicate that many reach the surface warm or cool enough to handle after some time, though conditions vary with size and circumstance. The descent ends with impact into soil, grass, rock, snow, water, or built surfaces. The sound of this final arrival is often modest compared with the earlier atmospheric boom. A small meteorite may bury itself quietly in soft ground. A larger one may strike with a more noticeable thud or sharp impact. Yet even here, the event remains shaped by its long passage through air. The atmosphere has stripped away mass, broken the body apart, slowed it, cooled it, and spread its pieces across a broad corridor. What reaches the ground is only the surviving remainder of a much more energetic process. In this region, the falling fragment becomes a bridge between sky event and physical object. It is no longer the bright line that startled observers over the United States. It is matter descending through ordinary air, subject to gravity, drag, and wind, carrying on its surface the brief signature of atmospheric fire. Its motion grows quieter, slower, and less visible, yet more tangible. Somewhere below, a stone from space approaches the land, not in a burst of light, but in the last silent minutes of its descent. On the surface of the earth, a fallen meteorite first appears as an object of contrast. It comes from a bright event in the sky, yet when it is finally found, it is usually dark, quiet, and still. It lies in grass, soil, sand, snow, or stone like any other small rock, and yet it often carries visible signs that separate it from ordinary material of the ground. In this region, attention rests on the exterior of the recovered stone itself, on the features formed during its passage through the atmosphere and preserved at the moment it comes to rest. The most common outer feature is a dark surface coating known as fusion crust. This crust forms when the outermost layer of the falling body melts under intense heating and then cools rapidly during the final stage of descent. It is usually thin, often no thicker than a shell-like skin over the original material beneath. Fresh fusion crust is commonly black or very dark brown, sometimes with a dull sheen and sometimes with a slight glassy appearance. On a recently fallen meteorite, this surface may look smooth in places and gently uneven in others, depending on how the molten layer moved before it solidified. Fusion crust is not a layer added from outside. It is made from the meteorite's own surface material, altered by heat and then frozen into place. This is why the crust often follows the contours of the object closely. It can wrap over edges, settle into shallow hollows, and preserve the broad shape of the stone. If the object broke apart late in flight, some fractured surfaces may remain partly exposed and show less complete crust. These lighter broken faces can appear beside darker areas, giving the meteorite a mixed surface pattern that reflects the timing of its last moments in the atmosphere. The shape of a recovered meteorite varies widely. Some are rounded, some angular, some flattened, and some irregular in a way that suggests breakage rather than slow erosion. A compact body that travels through the atmosphere while losing its outer projections may become smoother than it was in space. Sharp corners can melt away. Protruding regions are often removed first by ablation, leaving a more softened outline. Still, not every meteorite becomes streamlined. Many retain awkward forms shaped by fragmentation and internal structure. Their geometry reflects both their history before arrival and the selective removal of material during entry. One of the most recognizable surface features on many meteorites is the presence of shallow thumbprint-like depressions called regmaglypts. These are rounded hollows that form as the outer molten layer is sculpted by airflow and uneven ablation. They may appear over part of the surface or across much of the stone. Their size and depth vary. On some meteorites they are subtle, visible only when the light strikes from the side. On others they are more pronounced, giving the object an appearance unlike most Earth rocks. Despite the familiar name, these depressions are not true finger marks. They are aerodynamic features formed during passage through the atmosphere. Colour alone is not enough to identify a meteorite, because many ordinary terrestrial rocks can also be dark. The difference often lies in texture and density. A meteorite may feel unexpectedly heavy for its size. This is especially true of iron-rich specimens. But many stony meteorites also have a compactness that stands out when lifted. The surface may be smoother and more continuous than that of weathered ground rocks, with fewer visible grains or pores. Fresh meteorites are usually not highly porous. They tend to feel solid and cohesive, shaped by melting and pressure rather than by slow weathering at the surface of the Earth. The exterior may also show fine lines known as flow lines, created when molten material moves across the surface under the force of the rushing air. These delicate streaks can be difficult to see without good lighting, but when present they reveal the direction in which the surface melt once travelled. In some cases they run gently backward from the leading face of the stone. They are not always preserved clearly, especially if the meteorite has weathered after landing. But in fresh falls they offer direct evidence of motion through the atmosphere recorded in the outer skin. Weathering begins as soon as the meteorite reaches the ground. Water, oxygen, salt, changing temperature, and contact with soil slowly alter the surface. Fusion crust may fade from black to brown. Fine cracking can appear. Iron-bearing minerals may rust, creating reddish stains or patches. In dry deserts and polar environments, meteorites can remain recognizable for long periods because the pace of weathering is slower. In humid climates, especially where vegetation and soil moisture are abundant, the outer surface changes more quickly. This means that a meteorite found soon after a fall may look very different from one that has rested on the ground for many years. Freshly fallen meteorites are sometimes described as having a thin smell of burned stone or metal, though such impressions vary and are not reliable for identification. Surface temperature also varies. The fusion crust forms under intense heat, yet the final descent through the atmosphere allows cooling. As a result, a meteorite is not usually glowing when found. Its outside may be warm, near ambient temperature, or cool depending on size, environment, and time since landing. The popular image of a blazing rock setting the ground on fire is not a normal description of ordinary recovered meteorites. Some meteorites show evidence of late-stage cracking, where the surface crust covers most of the body, but broken areas reveal lighter material beneath. A broken face may appear grey, tan, or metallic depending on the meteorite type. Yet in this region of observation, the interior remains mostly hidden. What matters here is that the exterior often tells a story of brief melting, rapid cooling, and passage through air, the crust, the smoothed edges, the shallow pits, the dense feel, and the unusual continuity of the surface all point to a journey unlike that of any ordinary earth stone. The setting in which the meteorite is found also shapes how it is perceived. On snow, the dark object may stand out sharply. In a ploughed field, it may be mistaken for an ordinary clod or industrial debris. In a desert, its crust may contrast with pale sand and make it easier to spot. On a roof, road, or driveway, it may be identified quickly because it appears out of place. Many meteorites are discovered not because they look immediately extraordinary, but because they appear where no one expects a stone to arrive from above. In this region, the fallen object becomes a surface record of atmospheric passage. The sky event is over. The sounds have faded. What remains is a small body of rock or metal whose outer skin preserves heat, airflow, melting, and descent in visible form. Before any cut is made or any laboratory test begins, the surface already offers clues. It shows that the object is not merely dark, but transformed. It is a fragment of the wider event reduced to stillness, carrying on its exterior the last visible mark of its arrival through the air. Beneath the dark outer skin of a meteorite lies a different region, one that no longer speaks mainly through shape or surface flow, but through structure and substance. Once the outer crust is broken, or a cut face is examined, the fallen object reveals patterns that do not usually belong to ordinary rocks found on the ground nearby. In this region, attention moves inward from the altered exterior to the material body itself. The focus rests on mineral grains, metallic phases, internal textures, and the broad classes scientists use to describe the different kinds of meteorites. Meteorites are commonly grouped into three main categories: stony meteorites, iron meteorites, and stony iron meteorites. This classification is broad, but it provides a useful first map of internal composition. Stony meteorites are made mostly of silicate minerals, which are minerals built from silicon and oxygen combined with other elements such as magnesium and iron. Iron meteorites are made mostly of metallic iron mixed with nickel. Stony iron meteorites contain substantial amounts of both silicate minerals and metal. These categories reflect differences in origin and history, but in this region the concern is first with what lies inside the stone itself. The most common recovered meteorites are stony meteorites. When a fresh interior is exposed, many appear grey, pale brown, or dark greenish grey, often with tiny reflective flecks of metal scattered through a finer rocky background. Some contain small round grains called chondrules. A chondrule is a tiny, once molten sphere that formed early in the history of the solar system and later became locked inside a larger body. Meteorites containing these round grains are called chondrites. Their interiors can look like compact stone sprinkled with minute beads, fragments, and metallic points pressed together over immense spans of time. Chondrules vary in size, shape, and composition. Some are nearly perfect spheres, while others are broken or slightly flattened by later processes. Under magnification, they reveal crystals arranged in delicate patterns that formed when droplets of molten material cooled in space. Their presence is one of the reasons chondrites are so important. They preserve some of the oldest solid material known from the solar system. In a hand specimen, however, they may appear only as tiny round spots embedded in the matrix, the finer material that surrounds and holds them. Not all stony meteorites contain chondrules. Some are chondrites, meteorites whose internal texture shows that they were once part of larger bodies that experience melting and differentiation. Differentiation is the process by which a body separates into different layers or regions because molten materials of different density move apart. In chondrites, the original round grains are absent or largely destroyed, and the texture may resemble some volcanic or igneous rocks on Earth. Yet their chemistry and mineral balance show that they come from worlds beyond Earth. The interior of such meteorites often looks more uniform, crystalline, and tightly interlocked than that of typical chondrites. Metal inside stony meteorites is often visible as small, shiny grains or irregular patches. This metal is commonly an iron-nickel alloy, a natural mixture of iron and nickel that formed under conditions very different from those that shape most ordinary Earth surface rocks. When a cut or broken face is polished, these metallic areas catch the light clearly. Their abundance varies. Some stony meteorites contain only scattered specks, while others hold more substantial metallic networks through the rocky interior. The combination of dense metal and silicate minerals is one reason many meteorites feel heavy for their size. Iron meteorites present a very different interior. When cut and polished, they appear metallic throughout, with a bright silver-grey surface that may later tarnish in air. Their substance is dominated by iron-nickel metal rather than stone. Many belong to the cores of ancient parent bodies that once became hot enough to separate into layered interiors, with metal sinking inward and silicate material remaining above, in a polished section treated with mild acid. Many iron meteorites reveal a remarkable interlocking pattern of metallic bands known as the Widmanstätten pattern. This pattern forms only when metal cools extremely slowly, over spans far longer than those available in ordinary industrial processes on Earth. The Wittgenstein pattern is not always visible in every iron meteorite, and it does not appear on an unprepared natural surface, but where it exists, it offers a striking clue to internal history. Broad metallic plates cross at characteristic angles, revealing crystal growth during very slow cooling inside a larger body in space. This is one of the clearest examples of how an interior structure can record not only composition, but also thermal history. The metal is not simply metal. It is metal arranged by time. Stony iron meteorites combine the two worlds. Some contain large transparent or translucent crystals of the mineral olivine set within a metal framework. Olivine is a magnesium-ion silicate common in both meteorites and parts of the Earth's mantle. Though the arrangement seen in some stony iron meteorites is unusual and visually distinctive, other stony iron meteorites contain broken rocky fragments mixed with iron-nickel metal in a more chaotic structure. Their interiors show that the boundary between rock and metal in space can take several forms, depending on the history of the parent body and any collisions it experienced. Internal texture matters as much as bulk composition. Some meteorites are fine-grained, with tiny mineral crystals packed tightly together. Others are coarse, with larger visible crystals. Some show signs of shock, such as darkened veins, fractured grains, or zones where minerals were transformed by sudden pressure during impacts in space. A meteorite is therefore not just a sample of matter, but a record of processes. Even before detailed chemical analysis, the interior can show melting, cooling, compression, breakage, and reassembly. Density and magnetism also reflect the inward character of the object. A meteorite with abundant metal may attract a magnet strongly. One with little metal may respond only weakly or not at all. Dense interior packing often distinguishes meteorites from porous industrial slag or volcanic rocks that may look similar on the outside. Even so, visual inspection alone is not always enough for certainty. Some Earth materials can imitate one or two meteorite features. What makes the true specimen convincing is the combination of properties silicate matrix, metal grains, unusual texture, high density, and mineral forms consistent with extraterrestrial origin. In this inward region, the meteorite becomes less an object of dramatic arrival and more a compact geological world. Its surface tells of atmospheric passage, but its interior tells of formation, alteration, and survival across deep time. Rock and metal lie together in ways that reflect early solar system conditions, parent body evolution, and violent collisions long before the fall over the United States ever took place. The cut face or broken interior opens a quieter history than the bright fireball suggests. It reveals order within the stone, and that order is the beginning of a deeper explanation of where the object comes from and what kind of matter has reached the Earth. Within the internal structure of a meteorite, chemistry becomes visible not only as a list of elements but as a pattern of relationships between minerals, metal, and ancient solid matter. In this region, the focus moves inward from texture to composition. The concern is with what the meteorite is made of at the elemental and chemical level, and with how that composition allows scientists to read conditions from the early solar system. The fallen stone, once seen as a bright disturbance over the United States and then as a dark object on the ground, now becomes a chemical archive shaped long before Earth took its present form. The most abundant elements in many stony meteorites are oxygen, silicon, magnesium, and iron. These are the principal ingredients of silicate minerals, which make up much of the rocky material in the inner solar system. Silicon and oxygen bond together in structural frameworks, while magnesium and iron enter those structures in varying proportions. This is why many common meteorite minerals are silicates rich in magnesium and iron. Olivine and pyroxene are especially widespread. Their relative abundance, crystal form, and internal chemistry help identify the type of meteorite and the processes it has undergone. Iron appears in more than one chemical role. In some meteorites it sits inside silicate minerals, bound with oxygen and other elements. In others it occurs as metallic iron mixed with nickel. This metallic component is one of the most distinctive features of many meteorites, especially when compared with ordinary surface rocks on Earth, where metallic iron is uncommon because oxygen and water readily alter it into oxides and other compounds. In a meteorite, the presence of native metal reflects the low oxygen conditions under which much of this material formed. It records a chemical environment different from the one that now dominates the Earth's surface. Nickel is especially useful because it is commonly associated with meteoritic metal and helps separate genuine meteorites from many look-alike terrestrial materials. The iron-nickel alloy found in meteorites often appears in small grains, thin networks, or larger masses depending on the meteorite type. Its abundance and distribution help define classification, but it also carries chemical information about cooling history and parent body processes. In iron meteorites, the ratio of nickel to iron and the presence of trace elements such as gallium, germanium, and iridium help scientists group specimens and infer shared origins. Sulfur is another important component in many meteorites. It often appears in the mineral troilite, an iron sulfide. Troilite forms rounded grains, irregular patches, or thin veins and commonly occurs beside metal. Its presence shows that not all iron in meteorites is metallic or tied up in silicate minerals. Some of it combines with sulfur under specific chemical conditions. The balance among metal, sulfide, and silicate phases helps reveal the environment in which the material condensed. Cooled, or later reacted on its parent body. In chondritic meteorites, chemistry preserves something especially valuable. These meteorites are often considered chemically primitive, meaning that their overall composition has not been drastically separated into core, mantle, and crust the way the Earth has. They contain a mixture of solid components that formed early and were later assembled into a larger body without complete melting. Because of this, many chondrites preserve a bulk chemical balance that resembles the non-volatile material of the early solar system. Volatile elements are those that evaporate more easily. In many meteorites, the pattern of which volatile elements are present or depleted helps indicate the temperature conditions under which the material formed or was altered. Calcium and aluminum deserve particular notice because they are concentrated in some of the oldest known solid inclusions found in certain chondrites. These calcium-aluminum-rich inclusions are small mineral assemblages that formed at very high temperatures near the beginning of solar system history. They are important because they represent some of the earliest condensates from the hot gas surrounding the young sun. In hand specimens they may be hard to recognize clearly, but under laboratory study they reveal a chemistry distinct from the surrounding matrix and chondrules. Their presence shows that a single meteorite can contain material formed under different conditions and later gathered together. Sodium, potassium, and other more volatile elements help trace lower temperature processes. If they are depleted, that may suggest heating or formation in a relatively warm environment. If hydrated minerals are present, that can indicate interaction with water on the parent body. Some meteorites contain clays or other alteration products formed when liquid water moved through the rock long ago. In such cases, chemistry records not only the early nebular environment around the young sun, but also later chemical activity inside small worlds. The stone thus preserves evidence of both original formation and subsequent change. Carbon also appears in some meteorites in striking ways. Certain carbon-rich meteorites contain organic compounds, carbon-bearing minerals, and very dark, fine-grained material. Organic compounds in this context are carbon-based molecules formed through natural chemical processes, not signs of life. Their presence is scientifically important because they show that complex chemistry occurs in space and on small bodies without biology. Some meteorites also contain water-bearing minerals, showing that both carbon chemistry and water-related alteration can exist together in ancient extraterrestrial material. This combination has made such meteorites central to discussions about how early Earth may have received some of its water and organic ingredients, though the exact contribution remains uncertain. Trace elements, present in very small quantities, are often among the most informative. Elements such as iridium, osmium, platinum, and the rare earth elements can serve as fingerprints. Their relative abundance helps distinguish between meteorite groups and reveals whether material has undergone melting, segregation, or impact mixing. Some trace elements prefer to enter metal, while others favor silicate or sulfide phases. By measuring where these elements are concentrated, scientists infer how matter separated and reassembled on the parent body. The chemical story is therefore not only about what elements are present, but about how they are partitioned among the minerals. Chemical composition also helps place meteorites within a larger picture of planetary formation. The Earth, Moon, Mars, and asteroids all formed from material in the protoplanetary disk around the young Sun. But not all regions of that disk had identical temperature, pressure, or chemical balance. Meteorites preserve samples from bodies that remained small, fragmented, or only partly transformed, because they escaped the complete recycling that reshaped planets. They retain chemical evidence of early conditions. Each elemental ratio and mineral assemblage becomes part of a map of how matter was distributed, heated, mixed, and altered in the first stages of solar system history. In this inward chemical region, the meteorite ceases to be merely rock or metal in a broad sense. It becomes a structured combination of elements, each placed in minerals, metal grains, sulfides, inclusions, and fine matrix according to ancient physical and chemical rules. Oxygen, silicon, magnesium, iron, nickel, sulfur, calcium, aluminum, carbon, and many trace elements together form a record of condensation, melting, alteration, and preservation. The fragment that once flashed across the American sky now opens into a deeper pass through chemistry, revealing not only what it is made of, but what kind of environment once shaped it, and how long that environment has echoed within the stone. Beneath mineral structure and chemical balance lies another level of evidence, one that is smaller than visible grains and longer than any human timescale. In this region, the meteorite is examined through isotopes, radioactive decay, and exposure history. These are methods that allow scientists to estimate age, measure change, and reconstruct how long the material has existed, how long it has remained part of a larger body, and how long it has travelled through open space as a smaller fragment. The stone that fell to Earth now becomes a clock, though not a single clock. It contains several kinds of time at once, each recording a different stage in its history. An isotope is a form of an element with the same number of protons but a different number of neutrons. Because isotopes of the same element behave similarly in chemistry, yet differ in mass or stability, they provide a powerful way to trace origin and age. Some isotopes are stable and remain unchanged over immense spans of time. Others are radioactive, meaning they decay into other isotopes at predictable rates. This predictable decay is the basis of radiometric dating, a method by which scientists estimate the age of a material by comparing parent isotopes with the daughter isotopes produced through decay. Meteorites are especially valuable for radiometric dating because many preserve minerals that formed very early in solar system history. Observations indicate that some components in meteorites, especially certain calcium-aluminum-rich inclusions, formed about 4.567 billion years ago. This age is among the oldest measured for solid material in the solar system. It does not mean every part of every meteorite formed at exactly the same moment. Rather, it shows that some meteoritic matter records the earliest known interval of solid condensation around the young sun. Different isotope systems are used for different purposes. Uranium decays through a sequence of steps into lead, and this decay can be measured in suitable minerals. Rubidium decays into strontium. Samarium decays into neodymium. Each system has its own useful timescale, chemical sensitivity, and preferred host minerals. By comparing results from multiple systems, scientists test whether a meteorite has remained closed to later disturbance, or whether heating, shock, or alteration has partly reset one isotopic clock while leaving another less changed. The aim is not simply to obtain one age, but to understand which event that age represents. There is a difference between formation age and later event age. A mineral grain may crystallize in the earlier solar system and preserve that ancient moment in one isotopic system. Later, the parent body that contains it may be heated by radioactive decay, struck by collisions, or altered by water. Such processes can rearrange some elements or grow new minerals. When that happens, certain isotopic systems may begin timing a later event instead. A meteorite can therefore contain records of original formation, later heating, and later impact disturbance all at once. Each age belongs to a different stage of history. Exposure age is a different kind of time. It does not measure when the material first formed, but how long it has travelled through space as a smaller body exposed to cosmic rays. Cosmic rays are high-energy particles that move through space and interact with atoms in the outer layers of meteoroids. These interactions produce new isotopes, known as cosmogenic isotopes, by breaking nuclei apart or transforming them. By measuring the abundance of certain cosmogenic isotopes or their noble gas products, scientists estimate how long the meteoroid has existed as a relatively small object exposed in space, rather than buried deep inside a larger parent body. This matters because a meteorite usually does not leave its parent asteroid immediately after the solar system forms. It may spend billions of years locked inside a larger body. Only later, often after a collision, does it break free as a smaller fragment. Once exposed, its outer layers begin accumulating cosmogenic signatures. An exposure age of a few million years therefore tells a very different story from a formation age of more than 4 billion years. The first measures its journey as an independent traveller through space. The second measures the much older origin of the matter itself. Some isotopes also help estimate how long a meteorite has rested on Earth. This is called terrestrial age. After landing, the meteorite is no longer exposed to the same cosmic ray environment it experienced in space, and certain unstable isotopes begin to decay away without being replenished at the same rate. In combination with weathering evidence and environmental context, this can indicate whether a meteorite fell recently or has lain on the ground for thousands or even tens of thousands of years. In deserts and polar environments, where preservation can be good, terrestrial age studies help separate fresh falls from ancient accumulations. Noble gases provide another subtle record. These gases, including helium, neon, and argon, can be trapped, produced by radioactive decay or generated by cosmic ray interactions. Their isotopic ratios reveal both deep age and exposure history. Because noble gases do not bond easily into minerals the way many other elements do, they behave in distinctive ways during heating and shock. A strong impact may drive some gases out. Gentle preservation may retain them. Thus, the gas content of a meteorite becomes part of the evidence for its thermal and collisional history. Short-lived radioactive isotopes are especially important for understanding very early solar system timing. Some isotopes present when the solar system formed decayed away quickly on geological timescales. Their daughter products remain as evidence that they once existed. By measuring these daughter excesses, scientists infer relative timing among early events such as condensation, melting, and differentiation. These methods show that some asteroids formed and heated rapidly in the first few million years after the earlier solids appeared. In this way, meteorites reveal not only absolute age but the pace of early planetary building. Shock can complicate isotopic interpretation. A major collision can heat minerals, fracture them, mix materials from different regions, or partially reset clocks. Water alteration can also move certain elements and disturb simple age relationships. For this reason, isotope studies require careful petrographic context, meaning the mineral and structural setting must be understood before the age is interpreted. An age is never meaningful in isolation. It must be linked to a mineral phase, a texture, and a physical event. The meteorite is not just dated. Its internal history is decoded layer by layer through several overlapping measures of time. What emerges from this inward region is a chronology with depth. The meteorite may contain matter that solidified near the birth of the solar system, spent immense spans of time inside a parent body, broke free after a later collision, drifted through space for millions of years, entered Earth's atmosphere in recent times, and came to rest on the ground perhaps only days before it was found. All of these intervals can coexist in one small stone. The dramatic fall over the United States is the briefest part of its history by far. In this region, atoms become records of duration, radioactive decay, cosmic ray exposure, trapped gases, and isotopic balance allow scientists to move beyond appearance and composition into time itself. The meteorite becomes measurable not only in grams and minerals, but in epochs. Its passage through the sky lasts seconds. Its descent to the ground lasts minutes. Its residence on Earth may last years or millennia. But the deepest time within it reaches back to the formation of the solar system. Preserved in isotopic signatures too small to see and too old to imagine directly, yet stable enough to remain inside the stone until it is finally read. Beyond the laboratory measurements of chemistry and isotopes, the meteorite points outward again toward the larger bodies from which such fragments come. In this region, the concern is with parent bodies, the original worlds in space that once held this material as part of a greater mass. A meteorite is rarely born as an isolated stone drifting alone through the solar system for billions of years. More often it begins as part of an asteroid or another small body, shaped there by accretion. Heating, melting, alteration, and impact. The fallen fragment over the United States thus leads back to an earlier setting, one where small worlds orbit the Sun and preserve different stages of planetary formation. Most meteorites that reach Earth are thought to come from asteroids. Asteroids are rocky or metallic bodies that orbit the Sun, most of them concentrated in the main asteroid belt between Mars and Jupiter. They vary greatly in size, from dwarf planet-scale objects down to bodies only a few meters across. Some remain relatively primitive, preserving material that never fully melted. Others were once heated enough to separate into internal layers, producing metallic cores, rocky mantles, and crust-like outer regions. Because of this diversity, asteroids are not a uniform population. They are a collection of different histories preserved in orbit. A parent body is the larger object from which a meteoroid fragment ultimately comes. The parent body need not still exist in its original form. It may have been broken apart long ago, its fragments scattered into families of smaller bodies. The meteorite found on Earth may therefore come not from an intact ancient world, but from the remains of one. Even so, its minerals and textures can still reveal whether that parent body once stayed cool and primitive, became warmed and altered by water, or grew hot enough inside to melt and differentiate. Primitive parent bodies are especially important because they preserve early solar system material with comparatively little large-scale internal reworking. Meteorites from such bodies often contain chondrules, fine matrix, metal grains, sulfides, and refractory inclusions that formed under different conditions and were later assembled together. These parent bodies may have experienced some heating, perhaps from the decay of short-lived radioactive isotopes, but not enough to erase all original structures. In them, the solar system remains recorded in a relatively raw form. The body acts less like a miniature planet and more like a container of early building blocks. Other parent bodies changed more deeply. If a body became hot enough inside, rock began to melt. Dense metal moved inward. Silicate liquids rose or collected separately. This process of differentiation created layered internal structures. A metallic core could form at the center, rocky mantle material above it, and crustal regions near the surface. Meteorites from such bodies reflect these internal zones. Iron meteorites are widely interpreted as samples of metallic cores or core-like regions. Achondrites often represent mantle or crustal materials from differentiated bodies. Stony iron meteorites may come from boundary regions where metal and silicate interacted closely. Heat within parent bodies likely came from more than one source. But an important early contributor was the decay of short-lived radioactive isotopes present soon after solar system formation. Bodies that formed early and grew large enough could trap this heat and warm their interiors substantially. Smaller or later forming bodies may have remained cooler. This means the timing of accretion mattered. Two bodies made from broadly similar starting material could follow very different internal paths depending on when they formed and how effectively they retained heat. The meteorites they later produced therefore carry evidence of both composition and thermal history. Water also altered some parent bodies. Certain meteorites preserve minerals that form when liquid water reacts with rock. This shows that some asteroids were not dry, inert stones throughout their history. Inside them, heat may have melted ice, allowing water to circulate through pores and fractures. The water changed original minerals into new hydrated forms and redistributed some chemical elements. These parent bodies were still small worlds, but they were chemically active for a time. Their meteorites record that activity in altered matrix, secondary minerals, and changed isotopic relationships. Collisions were constant agents of change. The early solar system was a more crowded and violent place than it is now. Small bodies struck one another repeatedly. Some impacts merely fractured rock. Others excavated deep material from inside a parent body and mixed it with near-surface debris. Still others shattered whole bodies into families of fragments. Shock veins, breccias, and mixed lithologies in meteorites preserve this collisional environment. A breccia is a rock made of broken pieces cemented or compacted together. In meteoritic form, it shows that the parent body was not always a quiet, intact object, but often a place of breakage and reassembly. Asteroid families seen today offer one clue to these ancient disruptions. When a larger asteroid breaks apart, many fragments continue orbiting the Sun on related paths. These groups, identified by shared orbital properties, are called families. Some meteorites reaching Earth are thought to derive from such fragments, which in turn trace back to a common disrupted parent body. The original body may have existed billions of years ago, undergone differentiation or alteration, and later been shattered. The stones that fall today can therefore be remote descendants of ancient collisions that transformed entire small worlds. Not every meteorite comes from the main asteroid belt. A smaller number are linked to the Moon and Mars. These are identified not by direct observation of launch, in most cases, but by chemistry, mineralogy, and trapped gas compositions that match those worlds. Powerful impacts on the Moon or Mars can eject surface material into space. Some of that material eventually reaches Earth. These meteorites are rare compared with ordinary chondrites and iron meteorites, but they show that parent bodies can include large differentiated worlds as well as asteroids. In the broadest sense, a meteorite is any natural fragment from beyond Earth that survives atmospheric entry, and parent bodies include multiple classes of solar system objects. Still, the great majority of ordinary falls over the United States and elsewhere most likely begin with asteroid parent bodies. These bodies are the leftover architecture of early planet formation, objects that never became full planets, yet preserve many of the same processes on smaller scales. They accreted from dust and rock. Some remained primitive, some melted and separated, some reacted with water, many were shattered. Meteorites are fragments of this larger population, selected by the accidents of impact, orbit, and survival. In this region, the fallen stone is placed back into a former world. The interior metal may once have lain deep inside a differentiated asteroid. The chondrules in a stony meteorite may once have rested in a primitive body that changed little after it formed. The hydrated minerals may tell of water moving through buried rock inside a small ancient world. Each parent body provides a setting larger than the meteorite itself and older than its journey to Earth. The fragment is therefore not only a sample of matter, but a surviving piece of a vanished or altered place in space, a piece of one small world carried across time until it reaches another. From the parent bodies in space, the path narrows again to motion. A fragment may exist for immense spans of time within an asteroid, but it does not reach Earth until orbital change brings it into a crossing path with a planet. In this region, the concern is with those orbital routes, the gradual and sometimes abrupt processes that move small rocky bodies from stable reservoirs into Earth-approaching trajectories. The meteorite that fell over the United States is no longer considered as a stone on the ground, or as a fragment inside a parent asteroid. It is now understood as a traveller moving through the architecture of the solar system under the rule of gravity. Most small bodies that eventually produce meteorites begin in the main asteroid belt between Mars and Jupiter. There they orbit the Sun in a broad population of bodies with differing sizes, compositions, and histories. Many remain on paths that do not intersect Earth. Their orbits are stable enough, at least over long intervals, that they circle the Sun without coming close to the inner planets. A meteorite-producing journey begins only when something disturbs that relative stability. The fragment, or the larger body containing it, must be nudged onto a new path. Collisions provide one kind of change. When asteroids strike one another, they break, shed fragments, and alter the motion of the debris. A collision does not need to send a fragment directly toward Earth. More often it changes the orbit slightly, enough to place the new body closer to a region of dynamical instability. Dynamical instability means that the gravitational structure of the solar system can then amplify small changes over time, gradually moving the fragment into more elongated or tilted paths. The collision is therefore often a first release rather than the whole journey. One important mechanism involves orbital resonances. A resonance occurs when an asteroid goes around the Sun in a repeating numerical relation with a planet, especially Jupiter. If the timing is such that gravitational pulls repeat in a regular pattern, the small effects can accumulate. Over time, the orbit of the asteroid or fragment can be altered significantly. Some resonances increase orbital eccentricity, which is a measure of how stretched an orbit becomes. As eccentricity grows, the path may begin to cross the orbit of Mars and later the orbit of Earth. In this way, a fragment that once remained safely in the asteroid belt can be guided into the inner solar system. Jupiter plays a major role because of its great mass. Its gravity shapes the asteroid belt deeply, creating gaps and unstable regions where long-term residence is difficult. These gaps are not empty by accident. They are places where repeated gravitational influence has removed or redistributed objects over long timescales. Fragments entering such regions can be driven onto new paths more readily than bodies in quieter orbital neighborhoods. Observations indicate that many meteorites reaching Earth likely pass through such resonant routes on their way inward. Mars also matters, not because it rivals Jupiter in mass, but because once a fragment's orbit begins to stretch, encounters with Mars can further modify its path. These encounters need not be direct impacts. A close gravitational passage can adjust the orbit enough to shift the fragment toward a near-Earth trajectory. The inner solar system is therefore not entered in one step. A body may move first from the asteroid belt into a Mars-crossing orbit, and from there, through repeated perturbations, into a path that also crosses Earth's orbit around the Sun. There are also thermal effects that matter for smaller bodies. One of the most important is the Yarkovsky effect, a very gentle force caused by uneven heating and cooling. When sunlight warms a rotating asteroid, the body later re-radiates that heat as infrared energy. Because the re-radiation is not always perfectly symmetric in time and direction, it creates a tiny thrust. Over short periods, this force is extremely weak, but over millions of years it can slowly shift the orbit of a small body inward or outward. This gradual drift can move asteroids or fragments into resonances that then alter their paths more dramatically. In this way, sunlight itself contributes to the delivery of meteorites. Once a fragment enters near-Earth space, its orbital life often becomes more complex and less stable. It may cross the paths of one or more terrestrial planets. Repeated gravitational encounters with Earth, Venus, or Mars can continue changing its orbit. Some bodies eventually fall into the Sun. Some collide with planets. Some are broken further by collisions. Others are ejected into different regions. The near-Earth population is therefore a temporary population in dynamic terms. Bodies do not usually remain there forever. A meteorite-producing fragment is part of this shifting inner population for only a limited span compared with the age of the solar system. The orbit itself determines entry speed and geometry. A fragment approaching Earth from a path similar to Earth's own orbit may enter the atmosphere at a relatively lower speed, though still extremely fast by human standards. A fragment meeting Earth on a more opposed or inclined orbit may arrive much faster. This speed affects how much energy is released in the atmosphere, how high the visible meteor begins, and how likely fragments are to survive to the ground. The angle at which Earth meets the incoming object also matters. A shallow atmospheric path may reflect a particular alignment between the object's heliocentric orbit, meaning its orbit around the Sun and the motion of Earth at the moment of encounter. Not all incoming objects are linked to well-identified parent bodies. For many meteorites, scientists can describe likely source regions rather than a single exact asteroid. The path from parent body to Earth often involves many steps: collision, small body drift, resonance, orbital stretching, planetary perturbation, and final encounter. During this sequence, the fragment may spend millions of years in transit, its exposure age, read later in cosmogenic isotopes, records some of this interval. Even so, connecting one recovered meteorite to one exact source asteroid remains difficult in most ordinary cases. Observations indicate broad source pathways more often than exact individual lineages. Meteor showers offer a different kind of orbital behavior, but most meteorites do not come from the fragile cometary dust that creates familiar annual showers. Shower meteors are usually tiny particles released from comets, moving in streams along shared orbits. They often burn up completely in the atmosphere and rarely produce meteorites. The stones that reach the ground more commonly come from denser, stronger asteroidal material. Their delivery system is therefore less about Earth passing through a dust stream and more about rocky fragments being slowly diverted from asteroid reservoirs into Earth-crossing space. In this orbital region, the solar system appears not as a static arrangement of planets and belts, but as a dynamic field of pathways. Gravity shapes motion continuously, tiny forces accumulate, collisions free fragments, resonances stretch orbits, planets redirect passing bodies. Sunlight itself adds a faint push over immense spans of time. The meteorite that eventually falls over the United States is carried by this long choreography before it becomes a flash in the atmosphere. It is a small body moving from one orbital regime to another, from relative stability to repeated risk, until Earth happens to be present at the point where the paths meet. This means that a meteorite fall is not an isolated accident detached from larger celestial order. It is the final local expression of a much wider dynamical process unfolding across the inner solar system. The stone reaches Earth because its orbit has changed enough, for long enough, that the planet and fragment arrive at the same place at the same time. In this region, the path is everything. A fragment from a parent body becomes an Earth-crossing traveller, and the quiet geometry of orbit becomes the hidden cause of the bright event later seen in the sky. From orbital pathways and parent bodies, the subject turns inward again, not toward the stone itself, but toward human awareness of it. In this region, the question is not whether space sends rocky material toward Earth, because it does, and has throughout the planet's history. The question is whether something unusual is truly increasing over the United States, or whether modern systems are simply noticing more of what was always there: the bright fireballs, the recovered meteorites, and the many reports can create a sense of sudden change. Scientific understanding requires separating a physical increase in incoming objects from an increase in observation, recording, and public attention. The Earth is continually struck by material from space. Most of it is extremely small. Tiny dust grains enter the atmosphere in vast numbers and burn away high above the ground. Larger particles create ordinary meteors visible at night. Still larger bodies occasionally produce bright fireballs and, more rarely, surviving meteorites. This ongoing influx is part of the normal exchange between Earth and the surrounding solar system. It is not a new condition. The atmosphere has always been the place where much of this material becomes visible. What has changed strongly in recent decades is the density of detection. A bright meteor that passes over the United States is now far more likely to be captured than it would have been in earlier generations. There are more people awake under light-polluted but camera-filled skies, more vehicles with recording devices, more home security systems, more automated sky monitoring networks, more satellites, and faster communication among observers. A fireball that might once have produced only a few local accounts can now generate many videos, instrument records, and coordinated reports within a very short time. The sky has not necessarily become much busier in the short term. It has become more thoroughly watched. This change in observational coverage affects perception in several ways. First, it increases the number of events that reach public awareness. Second, it improves the precision with which paths are reconstructed and meteorite falls are confirmed. Third, it gives isolated events a collective visibility that can make them feel more frequent. When several bright fireballs occur over a period of months, each one is now reinforced by images, maps, and public discussion. The human mind recognizes pattern quickly and often gives added weight to recent vivid events. This does not mean the pattern is false, but it does mean the interpretation must be cautious. Meteor camera networks have expanded in many regions, including parts of North America. These systems are designed to record bright meteors systematically. Their records, when compared over time, provide a more reliable basis for examining trends than anecdotal memory alone. Observations indicate that year-to-year variation in fireball counts can occur naturally, because of random clustering, observing conditions, seasonal factors, and the geometry of meteor showers and sporadic meteoroid populations. A brief period with several widely seen events does not by itself prove a long-term rise in hazardous incoming bodies. Public reporting platforms also contribute to the appearance of increase. When one fireball is widely discussed, attention rises and people become more likely to notice or report subsequent events. This feedback can amplify awareness. A person who has recently watched a video about a meteor is more likely to step outside at night, recognize a bright streak as unusual, and file a report. In earlier times, the same person might have dismissed the event as distant lightning, aircraft light, or something unclassifiable. Better recognition increases report volume without requiring a change in the actual rate of incoming objects. Weather and social patterns matter as well. Clear skies over densely populated areas produce more reports than cloudy skies over remote terrain. A fireball visible on a weekend evening may receive more eyewitness accounts than one crossing the same region before dawn on a weekday. The expansion of suburban and urban camera coverage means that bright flashes are now recorded from porches, roads, parking lots, and rooftops that previously had no automatic observers at all. These practical factors shape the modern record powerfully. At the same time, scientists do not assume that all apparent increases are illusions. The near-Earth environment is dynamic. Small fragments continue to be delivered from the asteroid belt through collisions, resonances, and slow orbital drift. Some intervals may indeed bring modest variations in the rate at which certain sizes of objects encounter Earth. Meteor showers also create predictable periods of increased visible activity. Though shower particles are usually too small and fragile to produce many meteorites. For larger sporadic fireballs, however, short-term fluctuations are expected simply because rare events do not distribute themselves evenly in small samples. Clustering in time can happen without a deeper change in long-term hazard. A rigorous answer therefore depends on the quality and duration of the record. To show a genuine increase in incoming fireballs of a certain size, scientists would need consistent observations over many years with known detection thresholds. They would need to correct for changes in camera coverage, reporting behavior, cloud conditions, and instrument sensitivity. Without those corrections, raw counts can mislead. An increase in detections may reflect the growth of the observing system more than the growth of the meteoroid population. This is a common problem in science whenever the tools of observation improve faster than the phenomenon changes. There is also a difference between global rates and regional attention. A fireball over the United States may feel locally significant, but Earth is a sphere constantly turning beneath the meteoroid environment. Similar events happen over oceans, deserts, polar regions, and other areas where few people see them and fewer cameras record them. A rise in public awareness in one country does not necessarily indicate a regional concentration of incoming material there. It often reflects the combination of population density, communication networks, and observational infrastructure. Scientists therefore approach the claim of something strange carefully. Observations indicate that bright meteors and meteorite falls remain part of a normal planetary background process. Modern systems are revealing this process with greater detail than before. It remains possible for particular streams, impact fragments, or statistical fluctuations to produce brief intervals of heightened activity, but such cases require specific evidence. The broader pattern usually points first to improved visibility. The atmosphere has always been receiving small bodies from space. What has changed most dramatically is the human ability to notice, record, compare, and remember each event. In this region, the meaning of alarm becomes more measured. Scientists are attentive because every well-recorded fireball is valuable data. It can reveal trajectory, composition, source region, and fall pattern. Alarm in this sense is not a signal of panic, but of sharpened interest, because the event can now be studied with unusual completeness. The seeming increase is therefore partly a story about the sky, and partly a story about observation itself. More objects may not be arriving in a dramatic new surge. More of them are simply crossing a continent equipped to witness them. Thus the question of why more are being seen leads not only to asteroids and atmospheres, but to cameras, reports, networks, and statistical care. The bright path over the United States enters human systems as much as natural ones. As those systems become denser and more responsive, the sky appears more active. What emerges is a calmer scientific picture, a steady natural influx made newly visible by a watching civilization, with real variation at times, but with much of the apparent increase arising from the growing sharpness of the human record. In the public imagination, a bright object crossing the sky can easily become a sign of immediate danger. The sudden light, the delayed boom, and the idea of material falling from space all carry a natural force of alarm. In this region, the focus turns to risk itself, to the difference between what is rare and what is threatening, between what is dramatic and what is statistically significant. The concern is with what scientists know about the hazard posed by incoming rocky material over the United States. How often different sizes of events occur, what kinds of effects they can produce, and where uncertainty remains. The first and most important fact is that Earth is constantly exposed to incoming natural debris from space. But the great majority of this material is too small to present serious danger at the ground. Tiny particles burn away harmlessly in the upper atmosphere. Small meteoroids create visible meteors and are consumed before reaching lower altitudes. Even among brighter fireballs, many leave no surviving fragments large enough to matter beyond brief spectacle. This means that the ordinary visible activity of the sky is not, in itself, evidence of unusual public danger. It is part of the normal filtering role of the atmosphere, which protects the surface by absorbing the energy of most incoming bodies. Risk changes with size. A very small object may create only a brief streak of light. A somewhat larger one can produce a bright fireball and perhaps a few meteorites scattered over a wide area. Larger still, An entering body may fragment violently in the atmosphere and produce a strong airburst, meaning an explosive release of energy in the air rather than a crater-forming ground impact. Only at still greater sizes does the chance of severe regional ground damage become more significant. The frequency of such events decreases rapidly as size increases. Small entries are common. Large destructive entries are much rarer. This decline in frequency with increasing size is one of the central patterns in impact science. There are many more small bodies than large ones in the near-Earth population. As a result, the atmosphere deals with modest incoming objects far more often than with dangerous large ones. A person may witness or hear about several bright fireballs over a lifetime and still never encounter an event that poses direct serious harm. The drama of a fireball therefore does not scale simply with hazard. A brilliant event may be visually striking and scientifically valuable while remaining limited in practical danger. Airbursts deserve careful attention because they illustrate this distinction clearly. When an incoming body breaks apart in the atmosphere, much of its kinetic energy may be released high above the ground. This can produce strong light, shock waves, and in some cases broken windows or minor structural effects over a broad area. Yet the energy has still been distributed through the atmosphere rather than delivered wholly to one point on the surface. Observations indicate that atmospheric breakup is a common outcome for bodies large enough to be dramatic yet small enough not to remain intact to the ground. In this sense, the atmosphere is both the stage of the event and a major source of protection. Meteorites that do reach the ground are usually small compared with the original incoming body. They may strike roofs, roads, fields, or buildings, and rare documented cases show that direct property damage can occur. There are also extremely rare accounts of human injury. Yet over the scale of a large country such as the United States, the likelihood of any one individual being struck by a meteorite is extraordinarily low. The fall area for surviving fragments is often a long but narrow-strewn field, and much of it lies over unoccupied land, water, vegetation, or built surfaces where no person is present at the moment of arrival. The pattern of land use matters here. The United States contains large urban populations, but it also contains vast open regions, mountains, deserts, forests, plains, and water bodies. A meteorite fall distributed across such varied terrain has many chances to end without direct human consequence. Even in developed areas, the actual physical cross-section of people compared with the area beneath the sky is small. This is one reason why the emotional intensity of these events is often out of proportion to their direct personal risk. The sky feels intimate during a fireball, but statistically it remains very large. Scientists evaluate hazard by combining several lines of evidence. They use telescopic surveys to estimate the population of near-Earth objects. They analyze fireball records, infrasound detections, satellite observations, crater studies, and recovered meteorites. They model entry behavior to understand how objects of different size, strength, composition, and speed deposit energy in the atmosphere. This allows them to place individual events into a broader context. A bright meteor over the United States may be unusual in local memory, but its significance is assessed by comparison with global rates and known size-frequency relationships. There is, however, real uncertainty at smaller size ranges because detection is incomplete and object strength varies. Two bodies of similar size may behave very differently depending on composition and internal structure. A dense iron-rich object can survive more deeply into the atmosphere than a fragile carbon-rich one. A cracked stony body may fragment earlier than a compact stony body. Entry angle also matters. Because of these differences, The hazard from a specific incoming object is not determined by size alone. Scientists often know broad statistical behavior better than they know the detailed outcome of any one event before it occurs. Uncertainty also remains in the catalogue of smaller near-Earth objects. Large objects are easier to detect and track because they are brighter and remain visible at greater distances. Smaller objects are much harder to inventory completely. Some approach from directions difficult for ground-based telescopes, including from near the sun's glare as seen from Earth. This means there is a practical limit to how much advance warning exists for modest but still energetic bodies. Even so, most of these smaller objects are far more likely to produce localized atmospheric events than civilization-scale consequences. Regional impact risk over the United States is therefore best understood as low in any short human timescale, though not literally zero across geological time. Earth's surface everywhere has been shaped by impacts over its long history. The United States is not exempt from that planetary reality, but neither is it uniquely singled out in a way that current evidence supports. A fireball over one part of the country draws notice because millions of people live beneath connected skies and recording systems. The event feels immediate and local, yet the underlying hazard belongs to a global natural process. Preparedness in this context means observation, modelling, and communication rather than daily personal fear. Scientists remain alert because each well-recorded event improves understanding of atmospheric entry, object strength, and fall prediction. Surveys of near-Earth objects continue because larger hazards, while rare, deserve early detection. Public attention is useful when it leads to accurate reports and recovered meteorites. It becomes less useful when it turns ordinary statistical rarity into a sense of constant looming catastrophe. The measured view recognizes both realities at once. Incoming rocky material is real, and severe personal danger from ordinary fireballs remains very uncommon. In this region, rarity becomes the central fact. Bright events are uncommon enough to feel extraordinary, but not so uncommon that their appearance signals a new planetary crisis. Serious destructive impacts are much rarer still. Scientists are attentive because the subject concerns natural risk, planetary history, and the behavior of bodies crossing Earth's orbit, yet their attention is usually calm, numerical, and comparative. The sky can produce startling moments over the United States, and some of those moments merit close study, but the wider pattern remains one of low probability for major harm, moderated by the atmosphere and by the immense scale of the Earth, beneath a continuous but mostly gentle rain of material from space, above the United States and above every other part of the Earth. The sky is never entirely empty. It appears calm for long stretches, marked only by stars, planets, cloud, and darkness. Yet the planet moves through a wider environment filled with dust, stones, and fragments left from the formation and long reworking of the solar system. In this final region, the focus widens again to place the strange object seen crossing the American sky within that larger Earth space setting. The concern is no longer only with one fireball, one meteorite, one parent body, or one orbit, but with the continuous exchange between a planet with an atmosphere and the small debris that shares its cosmic neighborhood. Earth travels around the Sun on a path that carries it through a region occupied by countless small particles and occasional larger bodies. Some of this material comes from asteroids, some from comets, and some from collisions that continue to reshape small bodies over immense spans of time. The Earth is not waiting passively for rare encounters. It is moving through a field of natural debris all the time. Most of what it meets is tiny. Dust-sized particles and sand-sized grains enter the upper atmosphere constantly, adding to a faint and ongoing rain of extraterrestrial matter that usually passes unnoticed. The atmosphere is the first great mediator in this relationship. Without it, Earth's surface would receive far more direct impact from small incoming bodies. With it, most material is transformed before it ever reaches the ground. Dust grains slow and heat. Small meteoroids burn away. Larger meteoroids become visible fireballs and often fragment high above the surface. The atmosphere is therefore not simply the place where meteors are seen. It is the active boundary where cosmic debris becomes light, heat, sound, vapor, and sometimes stone. Much of what reaches Earth from space arrives not as intact objects but as altered matter dispersed through the air. This constant exchange is part of the natural condition of a planet orbiting within a developed solar system. The Earth gathers material from space, just as it sheds material through impacts that can launch fragments outward under rare conditions. On the Moon and Mars, impacts have sent rocks into space that later reached Earth. On Earth, the atmosphere and active geology erase much of the visible long-term record of smaller impacts, yet the process continues. Each bright event over the United States is one local sign of this broader circulation of matter among planetary surfaces, asteroid fragments, and orbital pathways. The scale of this exchange spans many orders of size. At the smallest end are microscopic particles that settle through the atmosphere and into oceans, soils, and ice. Some become part of sediment. Some dissolve or alter chemically. At the larger end are the rare bodies capable of creating regional destruction or global consequences, though those belong to far longer timescales than ordinary human experience. Between these extremes lie the fireballs and meteorite falls that attract scientific attention and public notice. They are large enough to become visible, yet usually small enough for the atmosphere to control much of their energy. In this middle range, the Earth-space relationship becomes observable without usually becoming catastrophic. The United States serves as one viewing ground within this planetary setting. Its wide geography, varied climate, instrument networks, and large population make it a place where many atmospheric entries are noticed and recorded. But the process itself is not national or regional in origin. It belongs to the whole Earth. Fireballs occur above oceans, deserts, polar ice, forests, islands, and mountain ranges as readily as above suburbs or highways. The American sky is one portion of a global dome beneath which the same physical exchange unfolds. The sense of something specifically targeting one country dissolves when the event is placed in planetary context. This broader view also clarifies the meaning of scientific concern. Scientists are attentive not because each fireball signals a new crisis, but because each one offers a sample of a larger system that is otherwise difficult to touch directly. A meteorite is a piece of another world. A fireball is a natural experiment in atmospheric entry. An orbit reconstruction is a clue to transport through the solar system. The concern is therefore investigative rather than sensational. It arises from the rarity of well-observed events, the value of recovered material, and the chance to understand the relationship between Earth and its cosmic surroundings with unusual precision. The Earth-space environment includes more than solid fragments. It also includes sunlight, solar wind, magnetic fields, radiation, and planetary atmospheres, all interacting continuously. Against this wider background, meteoroids occupy a particular place. They are tangible carriers of history. They link the present sky to the earliest formation of planetary matter. They link orbital motion to mineral structure and atmospheric physics to deep time. When one falls over the United States and is later picked up from a field, a driveway, or a patch of grass, a small part of the solar system becomes briefly available to human hands. This exchange has also shaped Earth over geological time. Large impacts helped modify the surfaces of planets and moons throughout solar system history. Craters on the Moon preserve that record clearly because the Moon lacks atmosphere, liquid water, and active plate tectonics to erase them. On Earth, weathering, erosion, sediment burial, volcanism, and crustal recycling remove much of the visible history, yet impact structures still remain in some places. The current fireballs seen in the sky are gentle reminders of a process that once acted much more intensely during the early history of the solar system, when debris was more abundant and collisions were more frequent. In the present era, the planet moves through a quieter but still active cosmic setting. Small fragments continue to arrive. Most go unnoticed. A few announce themselves with sudden light. Fewer still leave recoverable stones. Each event compresses enormous history into a brief encounter. Material formed near the birth of the solar system meets the air of a planet shaped by oceans, weather, and life. Ancient rock is heated in seconds, slowed in minutes, found in days, and studied for decades. The timescales are profoundly uneven, yet they meet in one event beneath the night sky. Thus, the strange things seen crossing the United States are not strangers to Earth in the deeper sense. They are part of the environment through which Earth moves, and of the material history from which Earth itself emerged. They are reminders that the boundary between planet and space is active rather than absolute. The atmosphere glows because matter still arrives. Stones fall because ancient fragments still orbit. Scientists watch because these passages reveal the larger system in motion. And the sky, though often quiet, continues to carry signs that the Earth is not isolated, but embedded in a solar system where dust, rock, light, gas, and gravity remain in continuous relation. The night sky grows still again after the passage of light. Nothing in the fields, roads, rooftops, or quiet neighborhoods appears changed at first glance. Yet somewhere on the ground a small dark stone may now rest, carrying within it a history older than mountains, older than oceans, older than any living thing on Earth. Its arrival seems sudden, but its story is slow. It begins in dust around the young sun, passes through accretion, collision, heating, fracture, and orbit, and only at the very end touches the atmosphere of a planet already full of weather, water, and life. The bright event over the United States becomes calmer when placed in this larger frame. It is not an intrusion from outside nature, but one expression of nature at a wider scale. Earth moves through a solar system that still contains remnants of its own making. Most remain unseen. A few enter the air and briefly turn motion into light. The atmosphere answers with heat and sound, then returns to silence. The ground receives only what survives. Scientists study these moments because they connect the visible present to deep time. A fireball is brief, but the material in it is ancient. A meteorite is small, but the world it came from may once have held internal layers, water, metal, and heat. Each fall is modest in size and yet immense in meaning. It shows that the Earth is still in contact with the unfinished debris of planetary formation. So the strange thing crossing the sky is not only a warning, and not only a wonder, it is a reminder of continuity. Space is not empty distance above the world. It is the wider setting of the world itself. The planet turns beneath a quiet rain of old matter, and now and then, for a few seconds, that hidden exchange becomes visible.